Yes, so good afternoon, everyone, and welcome to our meeting today. May I get a quick confirmation if you can hear me from your end? May I get a quick confirmation if you can hear me from your end? Okay, good. Thank you very much. I've received the confirmation that I can be heard from your end. Today I'm using a Zoom version, which is not subscribed before. And therefore, this meeting will terminate in less than 40 minutes time. So I would just request that if the meeting, once the meeting terminates, we just log in again using the same login credentials. And apologies for the inconveniences. So I repeat, the meeting will terminate at some point in time. So I request that once it does terminate, then we log in again using the same credentials. So I want us to pick up from where we stopped last time. I think the class reps are also supposed to remind me at the end of our meeting here. I can share the slides for this presentation. I think I've not shared the slides for this other part. So if my memory is right, I guess we stopped at, we had already derived the expression for computing or calculating the characteristic impedance of the line, specifically the input impedance, Zin of the line. And we looked at a case whereby the line is lossless. And remember, we said that when the line is lossless, it means that R is equal to 0 and G is also equal to 0. And then, of course, in cases whereby the line is lossy, then we will have R not equal to 0 and G not equal to 0. So we had already gone through this, I think, the last time we met on a face-to-face basis. Now, today, I think is almost afternoon, but today I want us to begin by looking at a new concept that is called the reflection coefficient and the standing wave ratio. Okay, now remember that this is still under secondary parameters of a transmission line. We've already talked about the primary parameters, okay, which can also be used to assess the line performance, okay? The 4 primary line parameters, we talked about them. And so far we have been introducing or looking at the secondary parameters, okay? We are already aware of the propagation constant, gamma. We are aware of the attenuation constant, alpha. We are aware of the phase constant, beta. We are aware of the characteristic impedance, Z0. We are aware of now also in this case, now we're going to introduce in 2 more parameters, the reflection coefficient and the standing wave ratio. When power or signal is launched into a transmission line, if the line is lossy, then not all of the launched power will be delivered to the load. But if the line is lossless, then all of the power launched by the generator or at the input end will be delivered to the load. But even so, whether the line is lossless or lossy, not all power will be absorbed by the load. Part of it will be reflected back towards the source. Now, we have a factor that determines how much of the power is reflected back to the source. And that measure or factor is given by the reflection coefficient. And the reflection coefficient can be viewed from 2 perspectives. We have one which is calculated on the basis of voltage. We call it the voltage reflection coefficient. And then there is another one which is calculated on the basis of current. We call it the current reflection coefficient, okay? So we have 2 reflection coefficients. There is one that is calculated on the basis of voltage, which we are going to begin by looking at. We call it voltage reflection coefficient. And then the other one is defined on the basis of the current parameters. We call it current reflection coefficient. So the voltage reflection coefficient can also be defined at different positions along the transmission line. Now, the first definition that is represented in question 2.36 is a voltage reflection coefficient that has been defined at the load. Whenever we define the voltage reflection coefficient at the load, we denote, ordinarily the reflection coefficient is represented by tau, Greek letter tau. Now, when it is defined at the load, we usually add a subscript L, so we talk of tau L. So the voltage reflection coefficient at the load will be defined as the ratio of the voltage reflection wave, or sometimes you can call it the reflected voltage wave, to the incident voltage wave. Now, the reflected voltage wave will have the amplitude being designated as negative, V naught negative, because that one will represent the component traveling towards the negative what? Z direction. Okay. And the incident voltage wave, or the positive traveling voltage wave, will be represented in terms of an amplitude, which is what? Positive, V naught what? Positive. Okay. And so we will basically be having now the expression for determining the voltage reflection coefficient being given by what we have in question what? 2.36. Okay. This term on the numerator represents the backward traveling voltage wave, or the reflected voltage wave, V naught negative exponential gamma L. And the component at the denominator will be representing the component of the wave that has been launched into the transmission line. We call it the incident wave, or the forward traveling voltage wave. Okay. Now, if we were to just go for the magnitude of the reflection coefficient at the load, we will then just specifically go for V naught negative, and then we divide it by V naught positive. That one is if we go for the magnitude only. But if we determine it as a complex quantity with the magnitude and angle, we will also have to incorporate the exponential terms. Okay. Now, at your own free time, I want you to derive equation 237. This one is an alternative expression for calculating the reflection coefficient at the load. And how we get it is, you can go to equation 231, C and D. Maybe I can project them. I can project them here. You come to equation 231, C and D. These two equations here. Okay. And where there is V naught positive, you replace it with its equivalence. Remember, we have said that tau L is equal to V naught negative exponential gamma L over V naught positive exponential negative gamma L. Okay. So if we make V naught positive the subject from this equation, you will find that V naught positive will be equal to V naught negative exponential gamma L divided by tau L exponential negative gamma L. Okay. Then you substitute what? You substitute this expression here. So where there is V naught positive, you substitute the equivalence. And then now you do what? Once you do that, this expression will be having V naught negative, and this one has V naught negative. You solve these two equations simultaneously. When you solve those two equations simultaneously, you will now find that you will get this expression that is given here. you will get this expression that tau L will be given by ZL minus Z naught over ZL plus Z naught. But remember, where you have VL, which is the voltage drop across the load, remember to replace it with ZL times IL. That's from Ohm's law. The voltage drop across the load VL will be given by ZL times IL. I would want you at your own free time to just take maybe a pen and a paper and try to derive equation 2.37. And in case you're facing challenges, you can maybe let me know the next time we meet on a face-to-face basis. Okay, good. So we can then now move on to the next item. Okay, we can then move on to the next item. Now, please take note of the fact that the voltage reflection coefficient at any point on the transmission line can generally be defined then as the ratio of the magnitude of the reflected voltage wave to that of the incident voltage wave. The incident voltage wave is sometimes called the forward traveling what? Voltage wave. Now, you are also allowed to drop the word voltage here after you have mentioned voltage in the first case. But I don't prefer a situation whereby you are dropping the word voltage in all the definition, because then it will become ambiguous. Okay, it will become ambiguous. So generally speaking, the voltage reflection coefficient at any given point on the transmission line would then now be the ratio of the magnitude of the reflected voltage wave to that of the incident voltage wave or the forward traveling voltage wave. And so we can now have tau L as a function of Z. Okay. And here you also, now remember that this Z represents the position on the transmission line. It is a variable, okay? So it will be equal to V naught negative exponential gamma Z over V naught positive exponential negative gamma Z. We have replaced L with Z. We have replaced what? L with Z. And so it will be equal to V naught a negative over V naught positive exponential 2 gamma Z. But remember that at the end of the transmission line, Z will be equal to L, because we begin the transmission line when Z is 0 and L is also 0. That's at the start of the transmission line. Then as L increases, Z will also be increasing. At the end of the transmission line, the value of Z will be equal to L. But in between, the value of Z will be equal to L minus L prime. In between, the value of Z will be equal to L minus L prime. And so if we substitute that one into equation 2.36, then we will get now this expression here as the one for calculating the voltage reflection coefficient for the transmission line at any given point along the transmission line. Now, this value of L, you should be given, or you should have been given sufficient information to help you determine it. For example, if the transmission line, let's say the transmission line was 20 centimeters, that's the entire length of the transmission line, and L prime has been specified to be this point, maybe it can be at what? 5 centimeters, okay? And when we get to the end here, that will be the L, which will be equal to 20 what? 20 centimeters. At the end of the transmission line, L prime will also be 20 centimeters, because now we have traveled the entire length of the transmission line. The other reflection coefficient that is worth mentioning, members, is the current reflection coefficient. Good news is that once you have the voltage reflection coefficient, you can also get the current reflection coefficient, such that now the current reflection coefficient at any given point on the transmission line will just be the negative of the voltage reflection coefficient, provided you use the same point. So let's say we had computed the voltage reflection coefficient at this point, and you get a certain value of the voltage reflection coefficient. If you want to get the current reflection coefficient, provided it is the same point, you just take the negative of the voltage what? Reflection coefficient. And so the current reflection coefficient, assuming it is the load, will be defined by the negative of what? Voltage reflection coefficient at the load. And if you don't want to do that, then you will take the ratio of the negative traveling current wave, that is the reflected current wave, to the incident current wave. Let me, at this point in time, pause for 30 seconds to find out if there are questions. There are questions? Let me know if there are questions. Let me know if there are questions. In the meantime, we can type our names and admission numbers on the chat area there. Kindly let us type our names and admission numbers on the chat area. Let's type our names and admission numbers on the chat area. Have we done that? Have we typed our names and admission? Okay, let's continue typing our names and admission numbers on the chat area there, even as we continue. So already we have introduced important relationships that can help us calculate the reflection coefficient, whether using the voltage information or the current information. Now, the next parameter, remember, is also a secondary transmission line parameter, is the standing wave ratio. The standing wave ratio is usually denoted by S. You can do small s or capital S, or you can use SWR. SWR now must be capital. SWR for standing wave ratio. Now, the standing wave ratio is defined as the ratio of the voltage maxima to voltage minima, okay, or current maxima to current minima, okay? The standing wave ratio is given by the ratio of the voltage maximum to the voltage minimum, and it will approximately be the same as the ratio of the current maximum to the current minimum. And it will be given by 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient. It can also be shown that an alternative way of expressing the maximum value of current from Ohm's law will be the V max divided by Z naught, and the I minimum will be the V minimum divided by Z naught. We have also already derived the expression for the input impedance Z in, okay, from this equation 235. We have the expression of the input impedance Z in from equation 2.35. So from that expression of the input impedance, we notice that the point of maxima and the point of minima will occur respectively at the maxima and minimum of the voltage and current standing wave. Okay. Okay. That is to say, what happens here is this, that current flows as a result of potential difference. Okay. And when we want to determine the maximum value of the input impedance, we have to make the denominator a minimum. So we will divide the maximum voltage with the minimum current. And it will be the same as the standing wave ratio S multiplied by Z naught. So this is an alternative formula for working out Z in, provided if it is Z in maximum. And Z in minimum now will be the smallest value in the denominator, the smallest value in the numerator will be V minimum. We divide by the largest value in the denominator, which should be I max. And that one will be equivalent to Z naught over S. So we can get Z in maximum here using this equation or this, and Z in minimum using this or that. Okay, and those relationships can also be proven. Okay, now I want us to have visual illustrations of the standing waves on the transmission line. And I want us to begin by considering a case of a lossless transmission line. Now, for the lossless transmission line, like I said, R is equal to 0 and G is equal to 0. So we expect that the entire signal launched into the transmission line should be reflected back. We expect that the signal launched in the transmission line, 100% of it should be delivered to the load. Okay, you know, it is in the case whereby the transmission line is not terminated in a load. If it is terminated in an open circuit, we expect the entire signal launch to be reflected back. Okay, but in this case, we talk about lossless lines, so there are no losses within the transmission line itself. And so we expect that the entire power launched by the generator should be delivered to the load. Now, let us further assume that the termination in this case is a pure resistive load, okay, whose impedance is made equal to the characteristic impedance of the line, and it is 100 ohms. So the line is matched, okay? The line is what? Is matched. So when the line is matched, it means we expect maximum power to be delivered to the load. Now, let us also take note that VL, which is the voltage drop across the load, it has been given as 100 volts. That is root mean squared what? Value, okay? So the conditions that will prevail on this kind of a line we've been presented with are presented in figure 2.10. Now I want to explain figure 2.10 using simple what? Using simple terms, okay? We have in this particular case, two plots. The upper plot is the so-called voltage wave plot. So this voltage plot, so you're plotting a voltage waveform on the transmission line. And the lower one is the current plot. The lower one is the current plot, is the current plot. Now, the horizontal axis is the one that is used to represent the distance along the transmission line. And in this case, we have represented the distance along the transmission line by using two parameters. The upper scale is the so-called electrical length, beta times R. Beta is the phase constant. When you multiply beta with R, you get a quantity called electrical length, and electrical length is given in radians. Okay? But we also have an alternative way of expressing the length or the distance of a transmission line in terms of wavelengths. So there are two scales there, okay? There are two scales there, okay? The upper one is the electrical length in radians, and the lower one is wavelengths, okay? In lambda, okay? So if we begin from 0, this one will be a half pi radians, and it will be corresponding to a quarter wavelength. Pi radian will be corresponding to a half wavelength. 3/2 pi radians will be corresponding to 3/4 wavelength. And when we come here, where we will now have, we'll have 2 pi radians. 2 pi radians will correspond to 1 wavelength. 2 pi radians will correspond to what? Will correspond to 1 wavelength or a full wavelength. Now, if the line still continues, then you will have 1.5 wavelengths or 1.25 wavelengths. So you can have 1.25 wavelengths, 1.5 wavelengths, 2 wavelengths, 3 wavelengths, and so on and so forth. Okay. And on the electrical length scale, the beta L scale, you'll have 2 pi, okay, 2.5 pi, can have 3 pi, 4 pi, and so on and so forth. Okay. Now, when we come to the waveform, now let's take note of the fact that we have been told that the voltage drop across the load is 100 volts RMS. So you'll put 100 volts there for the load. Okay. And we can plot the scale here. Maybe let's say here is 75 volts. Down here is what? 50 volts, then 25 volts, 0 volts, and so on and so forth. So the voltage waveform will look like this, okay? And the way we have it here is whereby we've set it around the 50 volts, okay? And then when you come up here, we've set it around the 100 watt, around the 100 volts, okay? Now, take note of the fact that we can determine the magnitude of the voltage. We can determine the magnitude of the voltage. For example, we can, if you take this point, you can determine V max there. Okay. And I want us to take note of the fact that V max there will be corresponding to I minimum. It will be corresponding to I what? I minimum. When the voltage is maximum, current is minimum for us to maintain the same power. Okay, for us to maintain the same power. And like here, where voltage is minimum, now current is what? Current is maximum. I hope we are seeing that. Here, voltage is minimum, current is what? Maximum, and so on and so forth. If you look at this waveform, you will notice that it is repeating itself. Okay, let's look at the waveform. It is repeating itself. Okay, and it is repeating itself after what distance in wavelengths? The waveform is repeating itself after what distance in wavelengths? Check where you have a full cycle. Then get the space between the two. It will be repeating itself after every half wavelength, isn't it? Okay. It will be repeating itself after every half wavelength. So this is the voltage and current wave patterns on a lossless transmission line, which has been terminated to a resistive load. So this one here is for the current plot. Okay, we've taken the maximum value of current to be 2 amperes, and then the minimum value down here to be what? To be 1 amperes, or to be 1 ampere, sorry. This one, when you interpret it directly, you will just take this 100 and divide by 50. So when you take 100 and you divide by 50, it will give you the maximum 2 amperes, which we are capturing here. Okay. And when you take this 100 and you divide it by 100, you get this 1 ampere, which we are capturing there. Okay. Okay, good. Now I want us to have a look at a new item on power flow along a transmission line. Power flow along a transmission line. Now, there are different types of powers. We have mean power or average power. Okay. Okay. Now, the average input power can be specified at any given point along the transmission line using equation 2.41. Okay, using equation 2.41. So if we look at equation 2.41 members, the average power launched into a transmission line, or the average power in a transmission line at a distance L, sometimes you can also use Z, in this case we're using L, will be given by a half the real part of the phasor voltage as a function of length times the phasor, the conjugate, times the conjugate of the phasor current as a function of L. The real part of the phasor voltage as a function of distance R of the transmission line multiplied by the complex conjugate of or multiplied by the conjugate of the phasor current IS at a distance L along the line. But where you have read the voltage must be the same point where you have also read the current. Now, if we assume that the line we are looking at is lossless, then we can substitute, okay? We can substitute equations 227A and B into 241. Because looking at those equations, we already know the definition of Vs of L and Is of L, so we just take the conjugate. So let's go to equation 227, just for a quick reminder. Equation 227, okay. This is equation 227A, and this is equation 227B, okay. Question 227A, question 227B. Those are the two equations. This is for the voltage phasor, this is for the current phasor. You can replace Z with L. If you replace Z with L, you will have L here, L here, L here, L here. Okay, but we can go for the real part only. This exponent is complex, so we can go for the real part only. So in the present equation, therefore, we can go for the real part. So the average power will be equal to a half of the real part of V naught positive into exponential J beta L plus tau exponential negative J beta L times V naught positive, the conjugate over Z naught. This one here actually is the current. This one here is like the I naught positive conjugate. Okay, so take note that even here now, we are going to use the conjugate of the reflection coefficient. We are going to use the conjugate of the reflection what? Reflection coefficient. Okay, so take note, minus is here, plus is here. Okay, then if this one here is plus, we will have minus here. If this one is minus, we will have this one as plus. Okay, and this one simplifies to V naught positive is here and V naught positive is there. We can pull it out and have now a half real part of V naught positive squared over Z naught, this Z naught, into now 1 minus the magnitude of reflection coefficient squared plus tau exponential negative 2J beta L minus tau complex conjugate, or the conjugate of that, times exponential negative 2J beta L. Now, if we look at the last two terms here, because of the presence of the exponent, they will be purely imaginary. They don't have the real part. And so if we only go for the real value of power, which makes the contribution to the average power, then we'll now find that the average power is given by equation 2.42. That P average is V naught positive squared over twice Z naught into 1 minus the magnitude of tau squared. Now, there are some calculations which will require that you know that equation 2.42, so that you should be able to use it to calculate average power. But let me emphasize that it is not the only formula that is available to enable us calculate what? Average power. It is not the only formula. There are other formulas, okay? It's not the only formula, okay? Now, please take note of the fact that the first term in the previous equation, this first term in the previous equation, you know, when you open the brackets here, you will have V naught positive squared over twice Z naught times 1 minus V naught positive squared over twice Z naught times tau squared. So the first term, when you open the brackets, the first term will represent the incident power. We usually designate it as PI in the transmission line. And then the second term with the negative, when you open the brackets here, the second term with the negative will now represent the reflected power. We usually call it PR. Okay. And we usually have to, for the conservation, law of conservation of energy, the input power should be equal to power transmitted plus power reflected, or the transmitted power will be the input power minus the reflected what? The reflected power. PT is the transmitted power or the input power. It should be equal to the incident power, okay, minus the reflected power. The incident power minus the reflected power. Let us also remember that in this equation, the negative sign denotes the negative traveling what? Wave. Okay, the negative traveling what? Wave. Because we have a negative going wave, and so that's why we have the negative there. And so the component of reflected power will now be having negative because of the negative going wave, either voltage wave or current wave. Okay. Let us also notice from this same equation 2.42 that the power remains constant, and as we can see here, it is not affected with the length. You see L has disappeared, so it is not a function of length. So the average power in a transmission line is independent of length, okay? And in this case, it is because the line we have looked at is lossless line, so power will remain constant. But if we had considered a lossy line, then the average power, the value of the average power will be dependent on the position of on the line or the distance on the transmission line. But if the line is lossless, then the power remains constant throughout the length of the transmission line. Now, also, let us take note of the fact that the maximum power delivered to the load will happen when we have zero reflection, okay? And so in this equation, maximum power will occur when this value is zero. So maximum power will just be given by V naught positive squared over twice Z naught. That's when maximum power will be delivered to the load, when we have zero reflection. And for zero reflection, it means that the reflection coefficient tau will be equal to zero. Okay. Now let us have a look at some special cases of transmission lines. The first case that I want us to have a look at is a shorted line. When the transmission line is shorted, it means that at the load, we have removed the load and connected a short circuit. Okay, so we can always go to equation 2.34. We can always go to equation 2.34 here. And when the line is shorted, it means ZL is equal to 0. So you come and substitute ZL equals to 0 here. Okay, if it is a lossy line. But if it is a lossless line, you come here and then substitute ZL equals to 0 when the line is terminated in what? In a short circuit. So when the line is terminated in a short circuit, if we assume that the line is lossy, we go for equation 234. And now when you substitute ZL equals to 0 there, you will get J Z naught tan beta L. Remember, beta L is the electrical length. Now, the reflection coefficient and the standing wave ratio at the load in case of a shorted line will be, the standing wave ratio will be infinity, but the reflection coefficient at the load will be -1. Okay. And looking at what we have here, this one has got only the imaginary part, so it will be a pure what? Reactance. The nature of the characteristic impedance here, or the nature of the impedance here, now called short circuit impedance, because it is impedance obtained under short circuit conditions, will be purely imaginary or pure reactance. And it can be capacitive in nature, or it can be inductive in nature. And that one will all be dependent on what? The value of L. Okay, at some point of values of L, it will become inductive. At some point or a level of value of L, it will be capacitive. Now, figure 2.11a is indicating or presenting the changes in the input impedance Zin with the length L of the transmission line. Okay, with the length L of the transmission line here. I will come to this figure later on. I will come to this figure later on and explain it. I will come to this figure later on and explain it. Okay, let us look at the next case, which is the open circuited line. Now remember here, if the line is shorted, the reflection coefficient at the load is -1, and the standing wave ratio is infinity. Standing wave ratio is infinity. The standing wave ratio is infinity. Good. Now, the second case that we are looking at is the open circuited line. And remember, I said that for the open circuited line, we will have the entire signal launched into the transmission line being reflected back to the source. So there's no load connected, okay? So in this case, we call it the open circuit impedance, ZOC. And it will be equal to the limit of Z, the limit of Zin as ZL approaches infinity. Z open circuit will be given by, from equation 2.34 for the lossy line, limit as ZL approaches infinity of that expression for Zin, and it will evaluate to Z0 over J tan beta L. Here we had J Z0 tan beta L. Here we are having Z0 over J tan beta L. Then you can multiply the denominator by J and multiply the numerator by J. In short, multiply by J over J. It will change it to negative JZ0. 1 over tan beta L is cot beta L. So it will be negative JZ0 cot beta L. And in this case, the standing wave ratio will still remain infinity the way it was there, but the reflection coefficient at the load, instead of it being -1, it will now be +1 for the open circuited line. Okay, and the variations of Zin with L is still shown in figure 2.11. This one was 2.11a. Okay, the other one should be B now, should be B. Sorry for that. This one should be B. This one should be B. I'm sorry about that. That one should be B. Now, let us also take note of the fact that using equation 244a and 244a and 243a, get the product. Just take this equation and multiply it with 244a. Okay. If we multiply the two, we'll notice that Z short circuit times Z open circuit is equal to Z0 squared. Put in other words, and we will see this in there's a topic on ABCD parameters. I will still come back to this. It is as if we are saying that Z0 is also equal to the square root of Z short circuit times Z open circuit. And that one is a very, very powerful relationship. Very, very powerful what? Relationship. Now, the third case that I want us to have a look at, which is of course the last scenario that we can have as at the load end, is a matched line. Okay, of course, there's still another fourth case where we can have ZL, which is not matched to the line. But that one is usually not desirable because it will not allow for maximum power transfer to take place. So ordinarily, the recommended case is usually where we have ZL having a value equal to Z0. So that one is a matched what? It's a matched line. And that is what is usually desired in a practical case. So we let Z in to be also equal to Z naught as input impedance to be equal to Z naught. And we can easily prove that if you go to equation 234 and you substitute Z, where there is ZL, you put Z naught. It will reduce to this equation here. And now in this case, the reflection coefficient at the load will be 0, meaning now all the power incident or all the power transmitted in the transmission line will be absorbed by the load. So there will be 0 reflection. And the standing wave ratio will be 1. Okay? The standing wave ratio will be 1. Okay. So V naught will now be 0. And the entire of the wave is transmitted. In other words, the wave will be transmitted 100% with no reflection at all. The entire incident power will be fully absorbed by the load. And that is why what we usually term the maximum power transfer. So the maximum power transfer is only possible when the transmission line is matched. When we are done with this section, actually, the next subtopic will be transmission line impedance matching. And we look at the Porter wavelength, transformer matching, stub matching, and so on and so forth. Okay, you see, transmission line impedance matching. This is what we will be doing what? This is what we'll be doing next week. So next week, when we meet for transmission lines, we will do what? We'll do transmission line what? Impedance matching, okay? Then after we are done with transmission line impedance matching, we go to Smith chart, okay? Then we go to Smith chart. Now Smith chart, I will not teach online. Okay, please, you will excuse me for Smith chart. We will have to meet face to face, okay? But the next content is still possible to cover online if members would want we meet online. Okay, though for the next meeting, I may not maybe want us to meet online because probably I may start, I will definitely start Smith chart. But if we meet online, I will only teach the theory part of Smith chart, then leave the practical part we will do when we meet face to face because we will be drawing. Now, having said that, let me go back to, I have already, there's a question. Okay, good. Okay, if there's no question. Is there a question? Is there a question? Okay. If there's no question, then let's continue. Let's continue. So we now have the plots I was making a reference to earlier on is they are shown in figure 2.11. The upper plot is showing the case when the line is short-circuited, and then the lower plot B is showing the case when the line is open-circuited. Sorry about that interruption on my internet connectivity, so we can continue. Now, this one here is the Z short circuit, and we've seen the form. Sorry members about that. I'm using mobile data. Someone called me and disconnected my internet. Apologies for that. So let's then continue. I was explaining a very important point here, members, which I don't want to escape us. The upper plot is Z short circuit against the electrical length, but you can also put wavelength here in lambda. And the second plot is Z open circuit against the electrical length beta L, but you can also use what? You can also use wavelength lambda there. Now, in the case of the short-term circuit scenario, we will begin, look at the wave, the waveform. We'll begin when it is inductive during the first 90 degrees, okay? Then it will go to what? It will go to capacitive between 90 degrees and 180 degrees. Then become again inductive, okay? Then again capacitive, okay? And so on and so forth. If you can recall from geometry or from mathematics or from calculus, plots which look like this are for which trigonometric ratio? The tangent and the cotangent, isn't it? The tangent, okay? The tangent, okay? And the what? The cotangent, if you can recall from geometry or from calculus, okay? You see, the values are heading to infinity at predetermined points. Like here, this one will be heading to infinity at that point, heading to infinity this side. Then again, it will now be continuous in between, then head to infinity. Here will be a plot like this, a plot like this, okay? And the same story is here, the same story is there, okay? Only that when we have the open circuit scenario, now it will start by being capacitive, then it goes inductive. Capacitive, then it goes inductive. Here it starts by being inductive, then goes capacitive. Inductive, then capacitive, okay? So that will be, that is the plot, okay, of the Z short circuit against electrical length, okay, for the shorted line, and the Z open circuit against electrical length for the open circuited what? Line. And we have considered the lossless what? The lossless line. Okay, we've considered the lossless line. Finally, for today, let us take a look at example 2.3. Okay, finally for today, let us take a look at example 2.3. And remember, we are taking our cut 1 next week. Of course, probably maybe the class reps will advise me after discussing with members. We can have the days we can have the cut is either Monday evening or Monday in the afternoon or anytime between 2 and 6 p.m. Then Wednesday, anytime between, Wednesday it is anytime between 11 and 6 p.m. And if it is Friday, it can be anytime between 2 p.m. and 6 p.m. So class reps will discuss with the members. You let me know when you want the transmission lines cut next week. And remember also the control cut. So you will maybe see how you can fit the 2 cuts next week. I will need to get that time. The cut for control will cover up to the block diagram representation where we had reached. And the cut for transmission lines will cover up to this example 2.3 where we have reached. A certain transmission line operating at omega equals to 10 raised to power 6 radians per second has alpha equals to 8 decibels per meter. That's the attenuation, 8 decibels per meter. And the phase constant beta is equals to 1 radian per meter. The characteristic impedance Z0 is equal to 60 plus J 40 ohms and is 2 meters long. So L is 2 meters long, is 2 meters. If the line is connected to a source of 10 at an angle of 0 degrees volts, and the source impedance ZG is 40 ohms and terminated by a load of 20 plus J 50 ohms, determine A, the input impedance, 2, the sending end current, and 3, the current at the middle of the line. Now, members, allow me to mention something here quickly, even as we solve this question together. Looking at this load, we can see clearly that this is an RL what? RL load. If it was given as ZL equals to say, for example, if you have 20 minus J 50 ohms, then in this case, it will be RC what? RC load, okay? RC load. So in this case, we are dealing with an RL load. We are dealing with an RL load. So there are some preliminary calculations that we need to carry out. We first of all begin by recognizing that the attenuation constant has been given in decibels per meter, so we have to convert it to nepers per meter. Now, what we have is that 8.686 decibels is equivalent to 1 nepers, or 1 neper. Now, what about what we have here, which is 8 decibels? What will it be equivalent to? It will be 8 times 1 over 8.8 over 8.686 nepers. And because the decibel here is per meter, this one will also be nepers per meter. So we've begun by converting the given what? Attenuation factor or constant to nepers per meter, and we found that it is 0.921 nepers per meter. Then we can write down the propagation constant. The propagation constant is given by gamma equals to alpha plus j beta. So our alpha is 0.921, and our beta has been given in problem statement as 1 radian per meter. So we can plug it in there, and so we will be having our propagation constant. We'll be having our propagation constant in per meter. Okay, but we need to determine gamma times L. So let us determine gamma times L. The length is 2 meters, so we pick that value of gamma, then we multiply it with the value of L. It will give us that gamma L is now 1.84 plus J2. 1.84 plus what? Plus J2. Now, from mathematics, it can be shown that there is a formula for tan hyperbolic x plus jy. Okay. And I want you, maybe at your own free time, to refer to that formula, the formula for tan hyperbolic of x plus jy, and see how you use it to get this value. There are steps which have been skipped here. Okay. This one is your homework. Eh? You can consult your geometry and your calculus or mathematics for the formula for tan hyperbolic, the formula for tan hyperbolic x plus jy, and see how you can use it to calculate tan hyperbolic gamma L to get what? To get 1.033 minus what? Minus J 0.03929. The tan hyperbolic into x plus jy will be evaluated by using the exponents, okay? So at some point you will have the exponents. At some point you will have the exponents. Like you see here, this one is the real part. This one is purely real. Tan hyperbolic gamma L is exponential gamma L minus exponential negative gamma L over exponential gamma L plus exponential negative gamma L. This tan hyperbolic what? Tan hyperbolic gamma L. But you go this route, take no tan hyperbolic gamma L, given by this relationship. But you see, if you come here, members, and it is quite important we remember this, there is an alternative formula we can use here, of tan hyperbolic x plus jy, and in that formula, once you get it from the mathematical tables or from your geometry or calculus, where there is x, you will put this value, and where there is y, you will put the 2. When you work it out, confirm that you are getting that value at your own free time. Okay. So once you compute the tan hyperbolic gamma L, you now come with it to this equation and say Z in will be equal to Z naught into ZL plus Z naught, tan hyperbolic gamma L over Z naught plus ZL, tan hyperbolic gamma L. Okay. This one, I'm using this equation here. I'm using this equation because the line is lossy. I'm using this equation because the line is what? A line is lossy. If the line was lossless, we would have used this equation here. If the line was what? Lossless. Okay. But you see here, this line is lossy, so we use the gamma one here. And you can confirm again at your own free time that when you remember here, we were told here, we were not told whether the transmission line is lossless or lossy, but you see the fact that it has got alpha here, which is not 0, means the line is lossy, isn't it? That one means the line is what? Is lossy. So when you substitute and say the value of ZL we know, Z naught we have been given in the problem statement. This Z naught, ZL is here. If we substitute using the value of tan hyperbolic gamma L we have computed, confirm at your own free time that you'll get Z in to be equal to 60.25 plus J 38.79 ohms. Now the sending end current means the value of current when Z is equals to 0, and it is the I naught. It will specifically be given by this formula, the generator voltage VG divided by Z in plus ZG. So we've been given the value of the source voltage as 10 at an angle of 0 degrees. So we can just drop that angle, okay, and simply say 10 over Z in, you get it from here, plus ZG. We were given ZG in the problem statement as 40. So you bring in the value of 40. We already know how to work with complex numbers. We work it out. Kindly confirm at your own free time that it is 93.03 at an angle of negative 21.15 degrees milliamperes. Then to find the current at any point along the transmission line, we will need to determine the value of V naught positive and V naught negative. Okay. So that now I naught is the value of current when Z is equal to 0, and it is what already we have here. So we can quote it from there. V naught from Ohm's law will be given by I naught times Z naught. So we take this value of I naught, convert it to amperes, and multiply it with the value of Z naught converted to polar form. We will get this value of V naught. Then because we want, we were told here to determine now remember we want the current at the middle of the line. The sending end current we have already determined. The sending end current is here, we have already determined. So when you substitute into this formula, we'll find that V naught positive will be equal to a half V naught plus Z naught I naught. These equations, we had already quoted them earlier on. So it will just be a half into where there is V naught, put the equivalence, then Z naught times I naught. Work it out at your own free time, confirm if you are getting this value in volts. Then for the V naught negative, it will be a half into V naught minus Z naught I naught. Similarly, substitute here and confirm that when you work it out, you get this value. And there's a lot of work for you, members. Remember, I'm teaching online here. There's a lot of work for you here. Okay. Then the next item at the middle of the line, it means Z will be L over 2. So the entire transmission line is L equals to 2 meters. At the middle, we will be at 1 meter, meaning 2 over 2, 1 meter. So we come here at the middle of the transmission line, Z is L over 2. So 2 over 2 is 1. So when you take gamma times 1, because Z will be 1, it remains the same. You know, here it changed. Here it changed because we multiplied by 2. So that's why it changed to 1.84 plus J2. But in this case, we are not multiplying by 2. We are multiplying by 1 because it is midway the line. So the gamma Z there will just be 0.921 plus J1. And hence the current at that point on the line will be IS as a function of Z, meaning Z is equal to L over 2 there. It will be V naught positive over Z naught. This component here, that component represents the I naught positive. And then this component here represents the I naught negative. So it will be V naught positive over Z naught exponential negative gamma Z minus V naught negative over Z naught exponential gamma Z. You substitute, and then again, members, there's a lot of mathematics there once you substitute, because those are complex numbers. Okay. Just also note that J1 is in radians, and if you convert it to degrees, it will be J57.3 degrees. You can choose to change the mode of your calculator to radians. So if it is in degrees, you have to convert accordingly. At your own free time, confirm that if you work out this expression, you get this final value. And there's a lot of work there. There is a lot of work there. There's a lot of algebra there, computations there with the help of the electronic calculators, which I would want members to undertake at your own free time. I would want members to undertake at your own free time. So let's try that at our own free time. Okay. You begin by remembering the formula, mastering the formula, then you practice on how to work with what? Complex numbers. Now, this is the last slide. It is for exercise. So at your own free time, you can also try these questions as exercise. Thank you for being patient with me, members. I think we were supposed to be stopping by 1. Kindly ensure that you have noted your registration number and name on the chat area there. I will take a few questions if they are there, then we end our meeting. And thanks to everybody, thanks to the class reps for making this meeting possible. So, and as far as the transmission lines is concerned, our meeting for this week is taken care of. And so we will be ready to undertake cut 1 next week. I don't want the cut to interfere with our meeting next week. Please look for a time for the cut that is outside the meeting time. We will still have a meeting next week for transmission line class and control engineering class, and also have control engineering cut and transmission lines what? Cut. Let me pick a few questions if they're there. Let me pick a few questions if they're there. The notes I just want to share straight away, because members will also need them to revise. So let me share the notes straight away for transmission lines. Okay, good. It seems I don't have a question, or I didn't give members, right? Okay, I've allowed members to unmute themselves. If there's a question, is there any question? Is there any question, or I end the meeting there? there any question or I end the meeting there? Okay, probably seems there is no question there still. Any question? Okay. Okay. Then I hope we've noted our registration numbers and names on the chat area. If there is no question, then let's stop there. Let's end our meeting there. Thank you for making this time. Thank you for staying patient, staying patiently as you're waiting for me. Bye-bye for now. Enjoy the rest of your day. See you next time. Bye.